So many of you are getting there, right? What was this one? For 2 people, there are going to be 2 ways, okay? For 3 people, there were how many ways? 6. Ooh, let's change to a different pen. 2. Then 6, and then 24 is what we came up with there. All right, so as you're looking at it, and many of you got to this place of going, okay, you started listing all of these. And one group said, well, all right, we're going to start with all of them that start with A. So it's A, B, C, D, A, B, D, C, A, C, B, D, A, C, D, B, A, D, B, C, A, D, C, B. And then ended up finding, oh, there are 6 of them that start with an A. 6 then start with a B, 6 start with a C, 6 start with a D. So once you do that, you can realize, well, really all I need to do is find out this one. How many start with an A? Because it'll be the same number then that start with a B, same number that start with a C, same number that start with a D, same number that start with an E. But this isn't easy to do either. No. There's other ways you could think about this. So if I take this 24 and I say, well, I'm going to start right here. Here's my starting point. I could start with an A. I could start with a B. I could start with a C. I could start with a D. And if I did that, and then say, okay, well, from A, how many things could be next? 3. Because I'm going to have either B, C, or D. And then off of the B, how many options are there? 2, going to be either C or D. Off of the C will be either a B or a D. And off of the D will be either a B or a C. And then off of the C, A, B, C, all I got left there is D. A, B, D, C, A, C, B, D, A, C, D, B, A, D, B, C, A, D, C, B. So then each time I'm like, all right, A, then D, then it's either B or C. So I end up with 1, 2, 3, 4, 5, 6 different ones. You could use that same strategy for the 5 to just find one of the stems, right? Because then what would happen? I would have another layer beyond that. So instead of getting from here and having 3 options, I get here and there's 4. And then from each 4, there's 3. And then from each 3, there's 2. And then from each 2, there'd be 1. That's one way to go. Could also say, again, this is for the 4 people. How many things can be in first place? How many options do I have that could be in first place? You're starting out, you got 4 people. How many choices do I have for being in first place? 4. So that's first place. After you've got your first place person, how many people can be in second place? 3. Because we're looking, we had 4, then we had 3, then we have 2, and then we have, there's 1, so third place. So once you know first, second, and third, there's only 1 option left for fourth place. How do those numbers get me to 24? So back to your boards, keep thinking about this, 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 or if you want to, just list them out. But if we start doing this, that starts getting us to figuring out eventually, well, what if I don't know? Like, what if I throw a number at you, a big number like 12? Are you going to want to list them all out if there's 12? No. Some of you don't want to list them out because there's 5. So what someone looked at and stumbled upon with their calculator is if you did 2 factorial, or they did 2 exclamation point on their calculator, right? Factorial is that's 2. 3 factorial is 6. 4 factorial is 24. And factorial means you multiply that number, and then the number 1 less than it, and then the number 1 less. So down here we had 4, 3, 2, 1. So really what we were doing is 4 times 3 times 2 times 1, and we got 24. Which if you're looking at this tree diagram that we started with, now if I had 5, I would have 5 options for the first one, 4 options for the second one, 3, 2, and 1. Or in other words, that would be 5 factorial, which is 120. So again, as we're doing this, in looking at patterns, if I can find a way to not have to write everything out, because again, mathematicians by our nature are lazy, this then would be n factorial. Now it changes a little bit, so stay where you are. What if we say something like, well now instead of I want to put all of them in place, what if I want to say, well, how many ways can 3 people finish first through third? I could do the same way. I could say, well, I go like this, all right? How many people can finish in first place? Oh, you have 8 people in a race. How many people can finish first?
8.
There are 8 people who could finish in first. Now that I've got a first place finisher, how many people are left that could finish in second place? 7. And how many could finish in third? And I only care about those. So if I multiply 8 times 7 times 6, which someone's doing on their calculator right now, what is that?
336.
So in an 8-person race, so any of you that ever ran track in high school or in college, 8 people in a race typically, there are 336 different ways that they could finish first, second, and third. All right? So what that is called, it is called a permutation. That is when the order is important. Because is first place different than third place? Yes, it is. So if the order is important, it's called a permutation. And now here's my little slight rant on the fact that the English language messes with mathematics. Have you ever, in high school, did you ever have a locker that you were assigned, or maybe in sports, and then you went to it and you put this little thing on it and you locked it to keep people out? What did you do to open it? What did you enter into that thing to open that lock up? You entered a combination, which is wrong. Does it matter the order that you put the numbers in there? Yes, it should be a locker permutation. A combination is, we're going to do in a minute, that's when order does not matter. In a permutation, the order does matter. And so specifically, this is the formula for permutation, where n is the number of whatever things I have, like this case it's 8 people in a race, permutation sub 3, because I want 3 people to finish, or I want first, second, and third place. The way I would do that is I do n factorial, which is the larger number, divided by 8 minus 3 factorial. Now, can you do that in your calculator? Yes. It's actually easier to do by hand at first. Because I look and say 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. Down here, I have 8 minus 3 in parentheses, which is 5. And 5 factorial is 5 times 4 times 3 times 2 times 1. And I go, oh, reduce, 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 reduce. I have 8 times 7 times 6, which is what that number was over there. My pen is not registering. There we go. So that's how I would do a permutation. So as we go about and as we reach our end of the term, permutation is a concept that you're going to see if you take stats next. For our exam, basically in a scenario similar to this, using that formula, can you find out how many people there are? Where again, all you're going to have to do when in the end is do 8 times 7 times 6. All right. On your little handheld calculators, there is a factorial button that is on there. It's just a matter of like, do you know where it is? You should not be spending a lot of time looking for it. So it's better if you say, oh yeah, we had this formula, we did this, ta-da, that's our number. All right. Next items that you're going to do on the board. Now suppose you have the following number of people. How many ways can they be put into groups? All right, groups of 2. If I just want a group of 2, how many ways can I make just a group of 2? Does order matter with a group? Nope. So before, when we did, first, second, and third place, or first, second, third, and fourth place, the order matters. Now I just need a group of 2. So take some time with your groups at the boards and see if you can figure that out. On your marks, get set, go. So we have 1, 3, 6, and 10. All right, so again, it was 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So let's ignore n for a while. What if it was 6 people? But don't count it like we just did it. Look at these numbers. 1, 3, 6, and 10. Anything going on there? Take a look at those numbers. Do you see any patterns? What do you see, David? You would say the next number is 15.
That's 2.
That's going up 2. That one's going up 3. That one's going up 4. This would go up 5. This would go up 6. That'd be 21. So that is true. But does that get me now to an n?
No.
Not easily.
I just said it goes up by...
Yeah, it increases by 1, but that's how they actually derived the formula originally, which someone asked, isn't there a formula for that? That has the C in it? Yes. Combinations. Sorry, that's like right on the lip there. Go like that. Combinations, when order does not matter. So if the order does not matter, that's why I get all hung up on like, you don't put in a locker combination, you put in a locker permutation. If the order did not matter, put in any 3 numbers you want in any order you want and the lock should unlock, which is not how locks work. It's a locker permutation, but that's the formula for it right over there. So now we say, well, how many different groups of 4 can be made out of 6 people? That's actually a little harder to count than the permutations was. So instead, we're going to use the formula for I have 6 people, combination, I want a group of 4. So the process would be, I use the formula, n, how big is n? N is 6, so it's 6 factorial. All over r factorial, r is the second number, that's the 4th, right? Right there is the second number. And it's always going to be either this number and a smaller number or the same number. You can never have this number as a larger. Because you think about it. If I have 6 people, how many groups of 8 can I make? I can't make any groups of 8. All right, so then inside parentheses, I have n minus r, or 6 minus 4, factorial. So in other words, I'm going to have 6 times 5 times 4 times 3 times 2 times 1. That's times. In the numerator. In the denominator, I have 4 times 3 times 2 times 1. And then I have this, 6 minus 4. Well, 6 minus 4 is 2. So it's going to be 2 times 1 factorial. I start reducing. 4, 3, 2, 1. And then I can either multiply it or do more reducing. 2 goes into 6 3 times. So in the top I have 3 times 5. In the denominator I have 1, which is 15. There are 15 different ways that if I have 6 people, I can make groups of 4. So like when we started this class at the beginning of the term, I had our little cards out, and we usually had groups of 3. We had 14 people, and I was like, oh, how many groups of 3 can I have? 14 people, combination 3, 14 factorial divided by 3 factorial times 14 minus 3 factorial. The shorter hand way of doing this in the top, so I'm going to look at which of these, so like over here, this was the bigger number. Over here, this will be the bigger number. So 14 minus 3 is 11 factorial. So in the numerator, I'm going to have 14 times 13, that's not a 3, 13 times 12 times 11, but then it's going to be going 11, 10, 9, 8, so that's actually 11 factorial. And then the other number, this 3, comes down here and is 3 times 2 times 1. Those will be smaller numbers and easier to work with. So then I look and say, oh, 11 factorial, there's an 11 factorial. Those will reduce, leaving me with 14 times 13 times 12 divided by 3 times 2. Which again, you could do by hand, you can do in a calculator. I start looking and say, well, 2 goes into 12 6 times, 3 goes into 6 2 times. So then I have 14 times 13 times 2, which is a fairly large number. Be hard to do that by hand in terms of writing them all out. How many different ways could I make a group of 3? Which is why you typically never have the same group of 3 when you come to class. Does it sometimes happen? Sure. Do I look around to see, oh, that's the same group of 3 that it was last time? I bet you they switched cards. Because the probability that it happened would be 1 out of whatever that number is. All right? That's combinations. Combinations also comes up with when figuring out if you have so many teams in a league, like if you play in a softball league or something like that, and you're trying to play games. So if you have 10 teams and you're going to only play one team once, so it'd be 10 choose 2. How many different games would you need on the schedule if you had 10 choose 2? It'd be a lot of games so that you play each team exactly once. All right. As was pointed out, someone said, is it make sense that this is actually a triangle? And the answer is yes. And here's what it is. It is a figure known as Pascal's triangle. So this is Pascal's triangle, and it keeps going on. I can make another row below that, which I will in a minute. There we go. My next row down, and the way the rows work in Pascal's triangle is this number, if I look to the diagonals above it, 1 and 1, they add to 2. 3 comes from the 2 and the 1 adding up to get to the 3. That 4 was the 3 and the 1 adding up. The 6 was the 3 and the 3. So if I do another row down, I will have 1. You know what's my next number? 5. 10. 10. 5. And 1. Do another row down. It'd be 1. 6. 15. 20, 15, 6, and 1. These are the combinations. That's why Pascal's triangle, and when you were doing it, if you figured out, hey, this always kind of makes a triangle, it's because those values are related. So this is considered to be row 0. And this item right here, that column, would be column 0. Which means if I were to pick this number right here, I would look and say, okay, that's row 0. 1, 2, 3, 4, 5. That's the 5th row. So this would be combination 5, because it's the 5th row. And then as we go across, you can think of this as either column 0 or item 0. This is also item 0. This is item 0 or column 0. Column 0, column 0, column 0. 0, 1, 2, 3. So if we did, thank you. If we did 5, choose 2, longhand or with a calculator, it would give me number 10. So as I mentioned, one other option could be doing something like athletics, where you're talking about how many teams would there be if I had 10 teams. So now I need to have 10 rows. So that's row 5, that's row 6, 7, 8, 9, 10. This is 7. That's 21. This is 8. And that's 28. Because again, 7 plus, so again, 1 plus 6 is 7. 6 and 15 is 21. This is 9. 8 plus 28 is 36. This is 10. 9 plus 36 is 45. If I'm doing my adding correctly, this number right here would be 10, choose 2. Because it's the 10th column, 10th row down, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. But it's also, I can see that, no, it's the 10th row, because it's 10. First row, second row had the first number in was a 2. So first row, the first number in is a 1. Second row, first number in is a 2. So these all numbers go up. So that's how I know I'm in the 10th row. And then 2, that's a 0 item, first item, second item. So if I had 10 teams in some type of a softball league, and they're all going to play each other once. So I'm going to choose 2 teams. How many groups of 2 can there be? There are 45 groups of 2. I would need to have 45 games on the schedule if you play every team once. That is a lot of games. Right? Which is also why, like the NFL, they don't play everybody once. They play everybody in their division twice and then other people once here and there. Because there's no way you could have them play everybody once. We would never, there would always be a football game on. Not really. All right. So Pascal's triangle is what's called the binomial expansion. All right. Fun little fact. Pascal's triangle is used for actually quite a few things. Combinations are also part of, if I had, let's say I had x plus y to the 10th power. What would that be? Well, 10th power would be this row. So I'm going to finish out my, I don't know if I'm going to have all the numbers here, but I would have x to the 10th plus 10x to the 4th y plus 45x cubed y squared. See what I'm doing here? 1, 10, 45. And it would keep going its way down. Oh, sorry, no, that would actually be x to the 4th y squared. That's what I would have. Right? Because I'd have x to, again, why am I getting 4? That 10, that should be a 9. I'm getting myself all confused here. All my numbers going on. X to the 9th, y to the 1st. X to the 9th, y squared. And I would have, and then all these numbers that would go across this column, or this row, I should say, those are the coefficients. 1, 10, 45, all the way across till I get to the other side over there. For all my possibilities for x to the 9th, y, x to the 9th, y squared, et cetera, as I would go through that expansion. So that also is another way. So it's called, that's why it's called the binomial expansion, because there's 2 things, binomial, 2 items, Pascal's triangle. where we are going to look at it is something like this. Oh, this is a little bit different. Suppose you roll a die 4 times. What's the probability that it will be? Oh, no, this isn't what we're going to do. Yes. So think about this for a minute and don't answer out loud, but you're thinking. Suppose you roll a die 4 times. All right, so I'm like, all right, rolled it once, rolled it once, rolled it once, rolled it once. I'm thinking about a die. So, right. There's my dice, my die, single die. How many sides on a die? 6. So this is saying, what is the probability that if we roll it 4 times, there are no 3s? Well, first you have to say, well, if I roll the dice 4 times, how many different numbers could there be? Or the other way I could say this is, if I had 4 dice in my hand, rolled them all, how many different outcomes could there be? Nope. If I have 4 dice, right, each one of them has 6 options. So the first die has 6 options. The second die has 6 options. The third die has 6 options. The fourth die has 6 options. So probability is how many ways can I get what I want out of all possible outcomes? So if I do 6 times 6 times 6 times 6, that is my denominator. And what is that number? It's more than 6. 5,696?
No, 1,296.
Oh. I way heard that wrong. I'm like, 6,000, 5,000 sounds like a lot. 1,000, what's 296? That's better. Okay. If I roll 6 die at the same, 4 die. 4 die at the same time, there are 1,296 different things that could show up. So if I want no 3s, then I say, well, what would that look like? That would be, the first one is not a 3. So how would I write a probability of something being not a 3? Well, what is the probability of not being a 3? Well, there's a 1 in 6 chance of getting a 3. What is the chance of being not a 3? 5/6. What is the probability that the second one is not a 3? 5/6. 5/6. 5/6. So if I did that, 5 times 5 times 5 times 5 over the 1,296, that's the probability of having no 3s. And what's 5 times 5 times 5 times 5? Or 5 to the 4th? 5 to the 4th is 625 divided by 1,296. There's about a 48.2% chance, so just under half, that you roll 4 die and get no 3s at all. 48.225308642. Yeah. But I did 5 to the 4th power over 6 to the 4th power. That's what I get. It gets harder when I say, well, what if there's exactly 1 3? Do I care where that 1 3 is? Nope. So it's going to either be 1/6 times 5/6 times 5/6 times 5/6, or 5/6 times 1/6 times 5/6 times 5/6, right? Because this would be the first term is the 3. This is the second die is a 3, or it would be 5/6 times 5/6 times 1/6 times 5/6, or the same thing again, but then the last one's 1/6. But here's the thing. This, if you multiplied it, 1 times 5 times 5 times 5, That is, so this is all for exactly 3, or exactly 1, 3. Gonna keep going here. So that's 125 over 1296. This number, 5 times 1 times 5 times 5, is also 125 over 1296, and 125 over 1296, and 125 over 1296. And if they're all the same and one happens or the next one happens or the next one happens, we add those probabilities. And that's a rule of probabilities that you'll learn more about if you take the stats class next. Or in essence, I have 4 of them. Here there's only one way. Now there's one way. Exactly 1, 3, there are 4 ways. Exactly 2 3s, well, it gets a little bit more complicated. So again, is there a great way that I could do all of this? The answer is yes. It is known as the binomial theorem. The probability that an event will happen r times, so in our case, we'll look at an example in a second, in n trials, so n rolls of the die, n flips of a coin, n something else that happens, how many successes do I want? And then the probability of success is p. So find the probability of having exactly 3 5s when you roll a die 5 times. Lots going on here, so we got to make sure we pick apart the right parts. If I roll the dice 5 times, that's n, because it's the total number of trials. My success, what am I looking for? I want to get, this is my success. I want to get a 5. What's the probability of getting a 5 if I roll a dice once? 1 out of 6, because a die has 6 sides. So there's 5 trials. I want to get a 5. The probability of getting a 5 is 1/6. How many 5s do I want? Exactly 3. That's R. So if I'm talking about this, the probability that x equals 3, I want exactly 3 successes. 3 successes, that's my R. X is my unknown variable. Okay, this is like, how many successes do I want? That's X. I want 3 successes. Equals N, which is 5. 5 rolls of the dice. Combination 3, I want to have 3 5s. The probability of success is 1/6. It will be raised to the R power, which is 3. I want 3 successes. Times 1 minus P, that's failure. Basically, if it's not a 5, it's not a 5. There's 5 out of 6 of them, right? 1, 2, 3, 4, 6. There are 5 numbers that are not 5s. Raised to the n minus 2, or 5 minus 3, squared. So in other words, I want 3 successes. So successes to the 3rd power. I want 2 failures. That is, I want 2 of them to be not 5s. 2 failures. And then this is how many different ways, if I had 5 dice, I could have exactly 3 5s. It's my grouping. How many different groups of 3 can I have if I roll a die 5 times? And if I think back to the Pascal's triangle, or I could do it by hand. Let's just do it by hand. So this is going to be n factorial, 5 factorial, over r factorial, which is 3 factorial, times 5 minus 3 factorial, times, and then this will be 1/6, we're just going to leave it to the third, times 5/6 squared. Five times 4 times 3 times 2 times 1. In the denominator, 3 times 2 times 1, that's the 3 factorial. 5 minus 3 is 2, so it'd be 2 factorial, 2 times 1, times 1/6 to the third power, 1 times 1 times 1, over 6 times 6 times 6. 5/6 squared is 5 times 5 over 6 times 6. Now I just have a whole bunch of fractions. Start doing some reducing. Over here, I got my 3's, 2's, and 1's. 3's, 2's, 1's. Can I reduce anything else? Sure, this 2. Can reduce that 4 to a 2. And then I'm done. In the numerator, I will have 5 times 2. I'm not going to write the times 1, because anything times 1 is just itself. So I have 5 times 2 times 5 times 5 over 6 to the 5th power. 1, 2, 3, 4, 5 of those. The only thing I have down here is a 1. And at that point, you could plug that into your calculator. Now, if you have a graphing calculator, there is a shortcut for this, but that's not the scope of this class. If you remember how to do that from when you took it in high school, you're welcome to do that. So let's see, 5 to the third power times 2, which means there are 250 ways that I can get what I want, divided by 6 to the 5th, which is a large number, which means overall this probability is 0.032. Which means, probably the most important part, if I roll a dice 5 times, and in those 5 rolls, I have a 5 show up 3 times, there was only a 3% chance that that could have happened. Not very common.
I could get one to do it. I just need a little bit of shoe shine. Just
Really? Yeah.
down the corner.
Just, yeah. Make your die unfair.
No.
Mm-hmm.
No.
No, it's just bending the rules. It's not very
Exactly. It's making it so I can win.
It's called cheating.
Advantage? Are you really trying?
It's only cheating if you get caught.
No, it's not cheating if you get caught. It's always cheating.
You guys know what I just said.
That's right. But anyways, so there's a lot of things. So this gets into then a lot of the foundations for statistics. When we look at, say, all right, well, if we notice that something happened, which you're like, well, that doesn't seem like that should happen that often. What, is something wrong? Maybe they aren't fair dice. Maybe it isn't a fair coin. Maybe something isn't going on the way we thought it was. We look at it based on these theoretical probabilities. Like theoretically, that's all the times it should happen. Our family is big fans of the board game Settlers of Catan. Don't know if you're familiar with it.
Oh, yeah.
But on each of the placards, you have certain numbers that have higher values. So you can, like, certain resources happen. And there you're rolling 2 dice. So if I roll 2 dice at any one given time, how many different outcomes are there? Well, there's 36 because it's 6 times 6. And then you look and say, and if you look at it like, all right, well, what's the probability that, and the most common one, if you roll a 7, a sum of 7, it moves the robber, basically. But 7, a sum of 7 on 2 dice is the most common outcome, because it could happen as 1 and a 6, 6 and a 1, 2 and a 5, 5 and a 2, 3 and a 4, 4 and a 3. And that's it. There are 1, 2, 3, 4, 5, 6. So there are 6 ways that you can get a sum of 7 if you roll 2 dice.
A snake eye is 6 and 6, right?
A snake eyes is 1 and 1.
Oh, so wrong.
Yeah. So a snake eyes is 1 and 1, and that sum, a sum of 1 and 1, 1 plus 1 is 2. There is only one way out of 36 that you can roll a snake eyes. Yeah.
You can do it for sure.
I always get 1, so then you roll the
Anyone
dice.
got any dice? Anyone got any dice?
Okay, Professor, I have a question for you.
So now,
Flip a coin.
find the probability of having at least 1 5 when you roll a dice 5 times. This is different. So now if we're talking about at least 1 time, that means I need to find the probability. Let me change my color to black there. I need to find the probability that if I roll a dice 5 times, I have at least 1 5. So that'd be once, or 2 5s, or 3 5s, or, you guessed it, 4 5s, or 5 times. That's a lot. Well, what's missing up there?
6.
Can I have 6 5s if I roll a dice 5 times? No. So if I roll a dice 5 times, what are the different things that could happen for counting number of 5s? What's the fewest number of 5s you can have? 0. That's what I'm missing. If I were to add up all of these, it would add up to 1, because those are all the possibilities. So you could have 0 5s, 1 5, 2 5s, 3 5s, 4 5s, 5 5s. If I add all of them up, that adds up to 1, because that means everything could have happened. But if I'm looking at least 1 5, it's this. Well, if all of them together add up to 1, if I did 1 minus the probability of none, that is really messiness there. If I subtract the likelihood of none of them happening, that gives me the likelihood that something did happen. And that would be the easier way to go. So then this would be not 1 equals 1 minus, and then I use the binomial theorem. NCR, and I'll write it over down here again. NCR P to the R, 1 minus P to the N minus R. My N is 5 times. I'm rolling a dice 5 times. I want there to be 0 successes. I want no 5s. Times the probability of success. Getting a 5 is 1/6. That's to the 0 power. 5/6. I want all of them to be not 5s. Nope, not 6. 5. And again, N is the number of rolls, N is the number of trials, however you think. R is the number of successes that we want. P is the likelihood of whatever it is I'm doing that I want. I want to roll a 5, so that's 1/6. 1 minus P is the not 5. 1 minus 5, choose 0. Anything choose 0, if we think back to the Pascal's triangle, that was the left-hand diagonal that starts with 1. If I have 5 items and I want to choose I want to choose the 5 to happen never. How many ways can I have no 5s? There is one way. There's only one way that you can have no 5s. That is, they're all not 5s. Just like how many ways can I have all 5s? One way, because 5, 5, 5, 5, 5. Right. So there's only one way that can happen. So it would be then 1 times 1, this is 1, times something to the 0 power. Remembering our exponents, anything to the 0 power is 1. So I have 1 times this number. So I'll have 1 minus 1 times 1 times this, or just 1 minus 5/6 to the 5th power. And then you go to your calculator. 5 to the 5th divided by 6 to the 5th is 0.40 something something. Ooh, that's not what I wanted to do. Minus 1. Nope. I missed it. 1 minus 5 to the 5th divided by 6 to the 5th is equal to 0.598. So if I roll a dice 5 times, there's about a 60% chance that I'll see a 5 at least once. All right. Ready for the last one? Last slide for today. Very first problem, called the birthday problem. So if you have 20 people in a room, what is the probability that at least 2 people have the same birthday? What are some of your guesses?
That's not very likely.
Not very likely. So you throw a number on that. What do you think it would be?
8 billion.
No.
That,
Is that one of my best friends? like-
Give it to me as a percent.
like 0.0006.
0.0006, which would be
I think there's a 1.
0.06%. Someone said 1%. Someone said 20%.
What did I do?
All right. So here's how we would figure it out. Start with this. First, we have to have an assumption. Let's assume there are 365 days in a year. I mean, every 4 years there's leap day. We're just going to ignore that as an option. So let's just say there's 365 days. Okay? So let's say the first person comes in the room. Here's the first person.
How many people are we dating in all
We're going to have 20 people in a room.
of?
So first person comes into the room. What is the probability that their birthday is different than everybody else's? They're the first person in the room. It's certain. So what's a certain probability? 100%. As a fraction?
1/1.
1 over 1 or 365 out of 365. So there's 365 days to choose from. They get to pick. They are now in there. So their birthday is different than everybody else's. They're the only person in the room. That's my first person. Second person comes into the room. What is the probability that their birthday is different than everybody else that's in the room?
1 out of 364.
Well, this person's in the room. How many birthdays are left to choose from? 364.
364. So 1 out of 364.
No.
364 out of 365.
We still have 365 possible days, but that second person, and the reason why I'm going to go different is because if they're all different, 1 minus that means somebody has the same birthday. Could be one person, could be 2 people have the same, could be 2 people with the same birthday, could be 3 with the same birthday, could be 2 different sets of people with the same birthday. You could find out, oh, they do and they do. You could have 3 people with the same birthday. You could have 3 sets of 2 different people. There's a lot of different ways of going about it. But if I'm first going to find what's the probability, right now I'm finding the probability that if 20 people come in the room that they're all different. Well, the opposite of all different is someone's the same. So now what's the third person? what is the probability that the third person in the room has a different birthday than those two? 363 out of 365.
Make you guess real quick.
What's the fourth? 362 over 365. And we're going to keep going until we get to the 20th person. It will be something over 365.
Is it 94%?
It's actually 346 because this was the first. The second person is -1. The third person's -2.
You're right.
So the 20th person's -19. All right. These numbers in the numerator, if I just look at those, 365 times 364 times 363 times 347 times 346, and that's where I end, is actually part of one of the formulas we started with today. If I were to say 345 factorial over 345 factorial, those would reduce, leaving me just these numbers. And that is permutation. 365 permutation 20. Because that is, as a formula, 365 factorial over 365 minus 20 factorial, which would be 365 times all the way down to 346 times 345 factorial over 345 factorial. This is a gigantic number. Okay? So that's what's in the numerator. The denominator, what do I have? 365, 365, 365, 365. All of them are 365. So I'm going to have this number, big number, in the numerator, divided by 365 raised to the 20th power. And now I am calculating something way beyond the scope of what your phone can do. So I'm going to look up permutation formula on my computer, and it asks me if I want to do a permutation calculator. 365 is my n objects, 20 is my number. So in the numerator, I'm going to have 365 permutation 20, and that number is 1.0366 times 10 to the 51st power. That means I'd have to move that decimal 51 places. That's a lot. So then I'm going to look up binomial theorem calculator. And I need to, oh, that's not the one I wanted. Where is it? Binomial distribution probability calculator. There we go. Oh, I want to take that number and then divide it by 365 to the 20th power. Give me a second here.
I have a frame.
1.0366 times 10 to the 51st divided by 365 to the 20th, according to my calculator, is 0.5885. There is a 58.5% chance that if I have 20 people in a room, that they all have different birthdays. That's the probability that their birthdays are different. What's the probability that someone's birthday is the same?
Less than that?
If I do 1 minus 0.5885, because either they're all different or someone's is the same. There is a 41.15% chance that if I have 20 people in a room, at least 2 of them have the same birthday. It's really that high. Once you get to 30 people in a room, you're just over 50%. Actually, no, 30 people in a room gets actually closer to 80%. Yeah,
I have a friend back home.
That makes no sense.
yeah. Because what you're doing, you're not just saying only 2 people. You're saying, well, what if 3 people have the same birthday? What if 4 people have the same birthday? What if these 2 people have the same birthday and these 2 people have the same birthday? What if these 2 and these 3? There are so many ways that you could have all those other variabilities in there and although each of them are small, there's so many of them that they actually add up to be quite a considerable amount. But the likelihood of all of them being different, there's only a 58% chance that they're all different. That's not a very high percent chance. Again, if you were following my math and how we did it, and can trust that I can use a calculator correctly, but yeah, that's about right. I mean, I was going to guess we were somewhere around 40% when we started this. I've done this in many years, so. Yeah. So in a random grouping of 30 people, there's a pretty good chance at least 2 people have the same birthday. So I'm not a gambling person, but if I got into a room and had like 35 people, and I didn't know any of them, I would be like, hey, I got $20. It says exactly, there's at least 2 people in here with the same birthday. Good chance I'm going to win.
Who wants to know the casino?
My birthday is December 8th. Yeah. All right.